Okay. Today's lesson we're going to look at rational functions and points of discontinuity. What we need to be able to do is to determine the vertical asymptotes of a graph and to determine the holes of graphs of rational functions. One of the things we're going to need to focus on that you learn to do today is you learn to be able to write left-hand and right-hand limit statements. And you should be able to recognize the relationship between factored rational functions and where their holes are and where their asymptotes are. So let's talk a little bit about this to begin with. So if you remember, a rational function is any function of the form of f of x over g of x, where f and g are both polynomial functions. Since you can't divide by 0, the zeros of the rational function in the denominator will restrict the domain. And this is where we start with. So let's just have a little look at what is an asymptote and what is a hole. So a rational function is going to look like the function that we see here. It's going to look like this. It's going to have, possibly can have, a vertical asymptote like this one, a horizontal asymptote looking like this one. And if we notice here at this point, this is how we symbolize that this one here has a hole. So let's see what creates holes and vertical asymptotes. I'll just do a little bit of an explanation. So if we have a rational function, we can have, the rational function is going to be of the form f of x over g of x. Now, if our f of x has a linear factor, such as this one, then we are going to get a graph which will have this is going to give us a graph which will have a root at x equals minus 2. So we can see that this graph here is going to look something like this. This graph here is going to look something like this. If we have a linear factor in the numerator, then the graph will look like it has a root at that point, and it quite possibly will have a root at that point. If that root has a multiplicity, or which is even, then the graph is going to have a different look to it. If we have a multiplicity which is even, then the graph is going to have, here at x equals minus 2, it's going to have a turning point like this one. If the multiplicity is odd and larger than 1, it's going to have a horizontal point of inflection. So if we have a multiplicity which is odd and larger than 1, we'll get a horizontal point of inflection. So it's going to look like this. If it is even, we'll have a turning point. If it's 1, it'll pass through once, straight line. So that's what happens in the numerator. What happens when we get a linear factor in the denominator? This one's fairly straightforward. If we get a linear factor in the denominator, like this one, then we're going to get a vertical asymptote here at x equals minus 2. And what's going to happen for this function is it's going to look like this. We get a vertical asymptote. Now things start to get a little bit more complicated if we have a multiplicity there. So let's increase the multiplicity of that one to 2. And now simply going to happen is the shape of the graph is going to look like this. If the multiplicity is even, will look like this. If the multiplicity is odd, it's going to look like this. That's your basic idea. Now, problems occur when we combine them. So if we get a rational function which has the same factor in the numerator and the denominator, how is it going to look? How is it going to look? Is it going to have a vertical asymptote, or is it going to have a point of discontinuity, a hole? Well, it depends on the multiplicities of each factor. So in this particular case, we are going to have a straight line, which looks like this, that has a hole here in it. It's going to have a hole. But change the multiplicities and you'll get an asymptote. You may even change the shape of the line. Let me show you how to figure it out. Okay, so let me do it with this general example. Let's say, for instance, we have, let's do an example first. We've got x plus 2, x plus 2, x minus 3. And then the multiplicity here is 2. What we need to do with this one is always start off by figuring out which are the excluded values. So the excluded value for this one is x is equal to 2 as an excluded value. This will limit and restrict the domain. So this is going to have the domain x is not equal to minus 2. So what we can do then is we can simplify this. This will cancel that. So this will simplify to this. However, we still have to have the same domain. We still have to have the same domain. And in this case, what we're going to get is we're going to get a vertical asymptote at 2, and we're going to get at minus 2, and we're going to get a root at 3. So our domain won't change. Our graph is going to have a vertical asymptote at minus 2. And it's going to have a root at 3. We can also see it's going to have a horizontal asymptote at y equals 1. So the graph has to go like this. Let's do some examples. So for each of these, we're going to determine if there are any holes or asymptotes. So our first step is to factor. This is x plus 3, x minus 2. This is x plus 3, x minus 5. We can see that. So then we determine what the domain is. The domain will not include the values -3 and 5. We can see that in the factors in the denominator. So we see the domain, which values need to be restricted by looking here. We can't have -3 and we can't have +5. That will create a divide by 0. But what we can then do is we can cancel. Now, this function will look like this function, be the same function, as long as we keep the domain the same. So we have to restrict -3 and 5. What does that mean? Well, the factor that we see here is going to create a vertical asymptote at, so this is going to give us an asymptote at x equals 5. This factor here is going to give us a 0, x equals 2. Now, this part of the restricted domain is going to have to be represented by a hole. It's caused by these factors that we've deleted here, that we've cancelled out. This is going to give us a hole, x equal to -3, and the graph will have a hole in it. So we'll draw the graph of x minus 2 over x minus 5. They look the same, and then you just add a hole to it. So I'll do a quick sketch of that so you can visualize it. We have to have a 0 at 2. So we're going to go through here at 2. We're going to have a vertical asymptote here at x equals 5. And at -3, we have to have a hole. We also have to have a horizontal asymptote of y equals 1. We see that when we look at the lead coefficient here, it's going to be 1 over 1. We can see the lead coefficient. So in order to pass through all of these bits and pieces, our graph has to look like this. Then we have to have the hole at -3. So over here, we need a hole. And that is at x equals -3. And this is how our graph will look. Do another example. All right, what holes, what vertical asymptotes? So what we can see is the domain is going to be x does not include -1 because of this. And x does not include 2 because of this. That's the domain. If we simplify the function, we should be able to remove this one and one of these, this one and one of these. So we will get x minus 2 over x plus 1. But the domain still has to exclude x equal to 2. So we have to have a vertical asymptote. They always come first. If they're there, they create a vertical asymptote. Those are the strongest. So we get a vertical asymptote at x equals -1. We are going to get a hole. These are the next strongest, x equals 2. We don't have a 0 x equals to 2, even though we have this up here, because because the hole will exclude it. So the way that the graph is going to look for this one is we start with our vertical asymptote. These are the most powerful. Here at x equals -1. Again, we're going to have this horizontal asymptote at y equals 1. Now, we have to have, it looks like we have to have a 0 x equals 2. So the way this will look appear on the graph is we will have a hole at x equals to 2. And the graph will look like this. So it will look like it's going to try and pass through there. And if you graph it on your calculator, it look like it does. But it won't. When you try and find the value, it'll say it does not exist because it's a hole. So, in order of priority, asymptotes first, holes second, zeros third. Can't have a hole if there's an asymptote. Can't have a zero if there's a hole or an asymptote. Okay, one last one. Still, have a look at this one. Write a left-hand and right-hand limit statement as x approaches 2 for this for each of the following functions. So what we need to do here is we need to see what happens as we approach 2. So how does our function look? Let me just pause a second. All right, where were we? Yeah, so what we're going to do is we're looking at what happens when we get to 2. So we're going to do a little number line analysis of the signs. So here at 2, we need to consider what the signs are of the 3 different terms in the expression given. So this one here, this factor here is going to change sign to x equals 1, and that's there. So this one is going to be positive. This one is going to be positive from, let me put the numbers in, from 1 upwards. This one's going to be positive from -3. So let me put these ones in. So this one's going to be positive here. This one's going to be positive here. And this one is going to be positive here. So we are going to get positive, positive, positive. And at this side, we're going to get positive, positive, negative. So this is going to be negative here, and then positive here, and at this point not defined. So that means the graph is going to go towards infinity in that direction, go towards positive infinity at this direction, and have a vertical asymptote at x equals 2. So we can express this using left and right hand limit statements. So as x goes towards 2 from a value smaller than 2, f of x will go towards negative infinity. And the limit value as x goes towards 2 from a value greater than 2 means that f of x will approach positive infinity. One more example like this one. Let me do this one here. So we start with our number line like this. And we are looking in this question what happens as we go towards 2. So our critical values are going to be 1, 2, 2, and 4. This one is positive when we're larger than 4. Less than 4, it goes negative. This one is going to be positive when we are larger than 2. This one has a multiplicity of 2, which means it's always positive. Well, always non-negative. This one is positive when we are greater than 1. So either side of 2 we are going to be negative, 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 positive, 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 positive. So our result is going to be positive, negative. So the limit as x goes towards 2 from a value smaller than 2 of h of x is going to go towards infinity. The limit as x goes towards 2 from a value which is larger than 2 of h of x is going to go towards negative infinity. Okay, that's it.